Welcome to Lab 4, Oscillations. Introduction. Welcome to Lab 4. Today we'll be discussing oscillations and specifically of a mass attached to a spring oscillating in an arcing pattern and changes in both the x and y directions. This lab uses the principles of conservation of energy to create these observations. The purpose of this lab is to analyze the motion of a mass attached to a spring that oscillates as it moves. Models and fundamental physics principles. The main principles are Newton's second law and the energy principle. So the first equation that you see is just the conservation of forces. So force net equals the force of gravity plus the force of the system, and then force of the system is the kinetic energy plus the gravitational potential energy, and then plus the spring potential energy, and then those are further explained below. So the preview of the main results, the computer model accurately predicted the motion of the mass moving on a spring, and the energy principle is also confirmed. System and surroundings. The system is the spring, mass, and Earth, and there are no surroundings for this model. Here are my initialized variables for the experiment and the computational model. They are the same. So that's the ball mass, which is 0.402 grams, and that the ball's initial position and velocity vectors, and then also just our constants being laid out. And all of this is just how we started our model. Here's the details of the experiment. We used a video of a mass on a spring moving, and then we uploaded that video to Tracker and manually plotted the points of the center of mass. We then gathered data about the position and then moved that data into a CSV file. We then opened up WebPython to generate code to track the movement of the mass using the energy principle, and then attached that to the CSV file to analyze that data. And then we compared that WebPython model to our manual calculations. So here's more details of the coding. This just essentially shows all of the different movements and how we're calculating the force of gravity and the force of the spring and all the forces that we are needed to define and use the energy principle. So the similarities and differences between the data and the model. On the left, you just see it would be like the top screen on your WebPython, and it just shows visually the tracking of the ball pattern. And on the right side, you see the blue is the model and the red is the experiment, so you see very, very similar oscillating patterns being the same between the two. So possible sources of error for this experiment is human error in plotting the points, errors in coding, and then not accounting for other forces acting on the object that would affect how it's moving. What if and what does it mean? So I did all of my calculations, and my x position value is 1.6 seconds and the y position value is 1.5 seconds. This is very similar because they are approximately moving in the same distance in both directions, but in the x position you're moving for slightly longer and a little bit more. And then here is our other question, and the energy principle satisfied. This is a graph we developed, and yes, because all the arcs are accounted for. So essentially, if you take the combined total of any of those at one time, they all will equal delta E, and delta E is constant. It's the yellow line in the middle. It's at 0 the whole time. So you're not seeing it change, which is important because it's not at 0 actually, but you're not seeing it change and deviate, so that means all the energy is being conserved within the system at all times. So our conclusions for this lab is that the energy principle is conserved and that the computer and observational models were very similar, so our computer model can accurately predict the motion of the mass. Thank you for watching.